All right, let's see if we can give an alternative definition or see if we can describe a line using vectors and a parameter. So here's a line in R2, right? It's in the plane. And now let's see if we can extract some data from this line. So first of all, a line has points on it. In particular, it's got a point, let's call it x0. And really, a point and a vector with initial point at the origin and then pointing in the direction of this point, we can use the same notation, right? So let's say here's a point on the line, x0. I'm going to go ahead and say it's a vector on the line, right? Not the vector's not on the line, but the vector points to a location on the line is the best I can say. So we've got a vector that points to a location on the line, call it x0, and then let's let x be any point on the line, and let's use a vector to point to that location. So here we've got some point x on the line, and let's go ahead and draw a vector to that location. So let's say here's a vector x. And now if you look, if you've got x0 and x, then you can connect the dots with a line segment, and we know that a line segment is just as good as a vector, so there's some direction involved here. So we can go ahead and call this thing x minus x0, because if you just remember the tip to tail representation of addition, of vector addition, you've got x0 and then followed by x minus x0. So if I add this thing to this thing, the x0s cancel and I just get x. So to go from the origin to x is the same thing as to go from the origin to x0 and then go from x0 to x along, right, using this direction, x minus x0. So now, this thing, if we just translate it back to the origin, points in a certain direction. So let's go ahead and call this thing v. So now, these two vectors are parallel. That means this thing must be a scalar multiple of this thing. So we now know that x minus x0 is equal to tv for some real number t. So we've got x minus x0 is equal to tv, where t is just some real number, right? That's our parameter. So we've got a line we can see is determined by a couple of things. Number one, it's determined by a point on the line, and two, it's determined by a direction vector. So we can see that x is a point on the line if and only if x is equal to x0 plus tv. So here's your description, and in particular, if we want to be more precise, so it's all of the things of the form x0 plus tv, where t runs through the real numbers. So here's a parametric description of this line, right? We've got a point on the line and we've got a direction vector. So those two things, right, these two things are all you need to determine a unique line. And again, t is a bunch of real numbers, right? And here's how you think of this parameter. So what happens when t is equal to 0? Well, when t is equal to 0, you just get the point x0. So when t is equal to 0, right, here we are on the line. So maybe let's go ahead and draw a real line. So if we think about sliding along the real line, when we're right here at 0, right, then here we are at this point on the line. And then when x is equal, or sorry, when t is equal to 1, well then it's x0 plus 1v. So we'd be right about here. And when t is equal to 2, we'd be right about here. And in fact, if we start at 0 and move along the real numbers in the positive direction, then that means we're starting here at x0 and moving along the line, not in a positive direction, but in the orientation where this x0 plus tv is pointing in the same direction as v. Well, x minus x0 is pointing in the same direction as v. And then when t gets to be negative, right, when t is over here, then we start to move, quote unquote, backwards along the line. So now we move in a direction that's opposite of the direction vector v, right? If t is negative, then that means we're pointing in the opposite direction of v. So this is how you should think of the parametric form of a line. There is some motion involved here, right? As t runs through all of the real numbers, you can think of a particle traveling along this line, right? Parametrically described by time, t for time. Okay. All right, so we said one of the goals here was to be able to move from one form to the other and back again. So let's see how to go from standard form to parametric form. So ax plus by equals c, x and y are real numbers, and here we've got x equals x0 plus tv. Here x, x0, and v are all vectors. So let's look at the line. So here's a complete description of the line. So all of the ordered pairs in R2, x comma y, is such that x and y are related via the following equation. 2x plus y is equal to 5. So the old standard equation of a line. So here's what that line looks like when we graph it, right? Just 2x plus y equals 5. You can plug in a 0 and see the y-intercept is going to be 5. You can plug in 1 for x, and then you can see that y has to be equal to 3. So you can get 2 points using this relation, and then once you have 2 points, you can go ahead and draw the line. So now, if x and y, the real numbers, are related this way, then you can go ahead and solve for x or for y. I'm going to go ahead and solve for y because we won't have any fractions. So this thing tells me that y is equal to 5 minus 2x. So how can we describe all of these ordered pairs? I can write them as rows, or I can write them as columns to really emphasize that these are vectors. I'm going to go ahead and just write it as a column. So how do we describe x comma xy if it's on this line? Well, x comma y is really equal to x comma 5 minus 2x. That's what y is. So we just replace y with 5 minus 2x. And then you can go ahead and break this thing up. Like 0, 5, and then x and negative 2x. And then you can factor the x out. So really, you can describe the points on the line as 0 comma 5 plus x times the vector 1 comma negative 2. So x is free, so it can be anything. So remember, we changed the name of free variables, like not x, y, z, but we prefer things like r, s, and t. So I'm going to go ahead and use t. So really, x comma y is on this line if it can be written as 0, 5, right? So here's x0, right? That's the point x0. And then plus t times 1, negative 2. So here's your direction vector, v. So you can see 0 comma 5 is a point on the line, and so there's a vector that points to it. That's this thing, right? That's x0. And then you've got a direction vector 1, negative 2. So 1, negative 2. Here's the direction vector. We can see it's parallel to this thing. And now any point on the line, call it x. So if this thing is x, well then this thing is x minus x0. That's the vector from here to here. And now we know that x is equal to, and we know that x minus x0 is parallel to this thing. So it's got to be some scalar multiple of 1, negative 2. And we know when we add this thing to this thing, we're just going to get this vector here. So anything on the line L, right, any point x on the line L is going to be subject to this equation. It's got to be equal to this vector 0, 5 plus a scalar multiple of 1, negative 2. So this is how you go from standard form, right? So here's the standard form, and then we just converted it to parametric form. x0 is a point on the line, v is the direction vector. All right, here's a set given in parametric form, and we want to just make sure that we can identify this thing as a line. So can we describe all of the points in here, or all of the vectors, in the usual standard form? So we'll let S be the set of all vectors of the form 1, 3 plus t times negative 3, 6. So maybe we can see that 1, 3 is a point on the line, if we believe it's a line, and that the direction vector is negative 3, 6. We probably could have also taken 1, negative 2, right? We can think of these things as like rise over run, or run over rise, whatever. So what does it mean if I take a vector in this set S? What does it mean that x comma y, what does that look like? Well, if it's in here, it's got to be of the form 1, 3 plus t times negative 3, 6. Those are the things that live in here. And this is for some fixed t and r, so a fixed time t and r. So now if you multiply, scalar multiply and add, that means that x is equal to 1 minus 3t, and y is equal to 3 plus 6t. And so now you can take this thing and solve for t. So negative 1/3 x minus 1 is equal to t. And now if you know what t is equal to, then you can go ahead and substitute back in the equation with a y in it. So now y is equal to 3 plus 6 times this thing. So y is equal to 3 plus 6 times negative 1/3 times x minus 1. And now we've eliminated the parameter t. Now we've just got x's and y's, and this is about to look like standard form. So 6 times negative 1/3 is negative 2. Go ahead and work all this out. You get y is equal to 5 minus 2x. And in fact, that turns out to be the thing that we looked at in the last slide. So 2x plus y is equal to 5. So if x, y is in this set S, then that means x and y are subject to the relation 2x plus y is equal to 5. So that's exactly the standard equation for a line. So if xy is in S, then it's got to lie on the line. And we showed that if xy lies on this line, then you have to have a parametric representation. Coincidentally, we showed that the parametric representation for this thing was given by 0, 5, and then plus, I think, 1, negative 2t. So this shows that a line can have more than one parametric representation. And that stands to reason, right? This thing is a point on the line, and there are infinitely many points on the line. So you can pick infinitely many x zeros to be your point on the line, right? You've got options for that. And there are many ways to describe the direction negative 3, 6. You could also describe this as the direction negative 1, 2, or 1 comma negative 2, right? There are many options on how you can write a parametric representation for a single line.